You've probably used a tool like ChatGPT and had that moment where you just stop and think, wait, how on earth does it do that? I mean, it can write a poem, it can debug your code, it can summarize a 10-page article in seconds. It honestly feels like some kind of magic. Well, today we're going to pull back the curtain and see how the trick is actually done. And to really appreciate it, let's start with something these models can do that just feels like it should be impossible. Okay, look at this. On the left, you've got a whole news article full of descriptions and extra details. And on the right, a perfect bite-sized summary of the most important facts. A large language model, or LLM, generated that in literally a fraction of a second. It's kind of mind-blowing.
So this brings up the obvious, massive question. To summarize something, you have to understand, right? You have to get the main point, who's involved, what the core message is. So how in the world does a computer achieve that kind of deep comprehension?
And here it is. This is the big secret, the reveal behind the whole magic show. The machine doesn't understand language at all, not in the way we do. It's not comprehending, it's just calculating. So, okay, if it isn't understanding anything, then what is it actually doing? Well, the entire complex process boils down to one almost deceptively simple task. At its absolute core, an LLM is a prediction engine. That's it. Its primary job, given any string of words, is to just calculate the statistical probability of what the very next word should be. Everything else you see, the poetry, the code, the summaries, is just a side effect of it being really, really good at that one thing. You know, we've all seen this. You're typing a text on your phone, and it suggests the next word. An LLM is doing the exact same thing, just on a scale that is almost impossible to imagine. It's like an autocomplete that has read the entire internet. So, for example, you give the model this famous phrase. It then crunches the numbers on every single word in its vocabulary. And because it's seen this sequence from The Hitchhiker's Guide to the Galaxy countless times in its training data, it knows there is an overwhelmingly high probability that the next word is fish. Now, this is where it gets really clever. This simple mechanism, just predicting the next word, can be cleverly framed to solve all sorts of complex problems.
And this slide just illustrates that perfectly. Want to figure out the sentiment of a sentence? You just turn it into a fill-in-the-blank game. The model predicts positive because that's the most probable word to complete that pattern. Want to answer a trivia question? Frame it like a Q&A, and the model will predict Charles as the most likely next word. It's not answering anything, it's just completing a sentence. It's all just word prediction.
All right, so how does a model get so good at predicting the right word? Well, in a sense, it's the same way a person learns, by reading. But in this case, it reads an absolutely colossal amount of text.
The process is kind of ingenious. You don't need humans to sit there and label data for it. You just give the model a gigantic chunk of text, you hide one of the words, and you ask it, guess the missing word. It does this billions upon billions of times, and every time it gets one wrong, it adjusts its internal knobs just a tiny bit to get better. It literally teaches itself. And the scale we're talking about here is just staggering. 156 billion. That's how many tokens, you can think of them as words or parts of words, are in just one of the many datasets these models train on. This particular one, called C4, is basically a huge snapshot of the web.
And, you know, it's not just random web pages. The training data is often a curated mix, kind of like a balanced diet. This chart here shows a famous data set called the pile. You can see it's mostly web text, sure, but there are also big chunks of academic papers, books, and even dialogue. That variety is exactly what gives the model such a wide base of knowledge.
But, and this is a huge but, when you train a model on the internet, you train it on everything. The good, the bad, and the really ugly. That means it inevitably ingests copyrighted material, it absorbs private data, it learns all of our societal biases and stereotypes, and it picks up an awful lot of toxic and abusive language. This isn't really a bug. It's an inherent problem with learning from a messy human world. Okay, so the model's been trained. It can now calculate the odds for what the next word should be, but that still just gives it a list of options. How does it actually, pick one to use? So this leads us to a really fundamental trade-off. On one side, you can tune the model to always play it safe and pick the most probable word. This gives you really accurate, high-quality text, but it can also get pretty boring and repetitive fast. On the other side, you can encourage it to pick some of the less common words, and that's where you get creativity and surprise, but you also risk it starting to talk nonsense. One of the main tools we have to control this balance is something called temperature sampling. The best way to think of it is just as a creativity knob that you can dial up or down.
So here's how it works. If you set a low temperature, like you see on the left, it basically exaggerates the probability differences. It makes the model very greedy and almost forces it to pick the most obvious word. But if you crank the temperature up high on the right, it flattens everything out, making the less likely word seem more attractive. That's how you get the model to take some creative risks.
Another really popular method is called top case sampling. This one is a bit more straightforward. So as you see here, the model first figures out the odds for every possible next word. But then, instead of trying to choose from all 50,000 of them, it just takes the top K, say the top 40 most likely words. It throws the rest away, recalculates the probabilities for just that small group, and then picks one randomly from there. It's a really simple but effective way to stay creative without going completely off the rails.
So let's put it all together. You have a system that just predicts the next word. You train it on the internet, and you give it a knob to control creativity. When you scale that simple idea up to an astronomical size, well, the consequences are profound, for better and for worse.
175 billion. That's the number of parameters in a model like GPT-3. You can think of each one of those parameters as a tiny, adjustable dial representing a connection in the model's neural network. During training, all 175 billion of these dials get fine-tuned. It is this sheer, mind-boggling quantity that leads to what researchers call emergent abilities, these complex skills like coding or summarization that nobody explicitly programmed in. They just emerge from the scale.
But that same incredible scale also amplifies every single problem that was baked into the training data. Because the model is just a probability machine, not a truth machine, it can hallucinate and just make things up. It can be an engine for misinformation, it can regurgitate private data, it can reinforce our worst biases, and it can be used for some really toxic stuff. These aren't just bugs to be fixed, they are inherent consequences of how these models actually work.
And that leaves us with one last really crucial question. We've seen how a surprisingly simple foundation, just predicting the next word, can lead to this incredibly powerful and also problematic technology when you scale it up. It really forces us to wonder, what other abilities are just lying there dormant, waiting to emerge as these models get even bigger? What happens when the magic trick gets even more convincing?